So I'm going to be talking about weaponizing CVE-2023-2033 for remote code execution in Electron. So I'm Nick Copi. Who am I? So I'm an AppSec engineer at CarMax. I also do some independent security research on the side, a lot of bug bounty. VCU alumni, former cybersecurity club president there. RVAsec CTF reigning champion. So tomorrow you can beat me in the CTF and take the throne. Or not, we'll see. ThinkPad dual wielder, so there's an image there of dual wielding a couple ThinkPads. My site's up there if you want to look at any of my projects, or it has the link to my blog as well. And notably, I'm not a browser exploitation specialist, and this talk kind of covers my first time going into that space and seeing some success. So the problem incentive, what does this talk about? I mean, the title at the beginning, that's a mouthful. What does it mean? So the origin story for how this research began was that I'd found several DOM XSS bugs in the core functionality of an application. I can't disclose what it was because the reports aren't disclosed, of an application with a public bug bounty program. So I'd found a couple in the past. I'd got a feel for roughly what they pay out, and I kind of wanted to go for more impact. So the application had an Electron desktop app client for it. So my XSS payloads would run in the context of that desktop client if a victim rendered the vulnerable component of it in their desktop client. So I wanted to go for remote code execution in the desktop client using the XSS because it would show much more impact and I would get paid more. So I spent a lot of time reviewing the code of the Electron application, looking for like logic level bugs to get more permissions and pop a shell on the system, but unfortunately I didn't find any. But the version of Electron it was running an old, outdated Chrome version. So there's been quite a few publicly disclosed Chrome vulnerabilities in the last year. It's a decent chance that several of them can lead to RCE, but there's not like public, pre-built, full RCE payloads for those available. There's stuff that gets you part of the way there, and we'll get into that. But the point is I needed to take, for one of these potential bugs that could get remote code execution in that Chrome process on the victim application, I needed to build the RCE exploit to show impact in the bug report. So the reason this was necessary in the bug report, instead of just saying, you're running this old Chrome version, I could, in theory, get remote code execution. A lot of the times, when you're submitting reports, it's kind of like dealing with insurance fixers where they want to, if you don't have a proof of concept that shows, yes, definitively you can get RCE with this, I probably wouldn't get paid out for RCE. So I needed something built that showed that, yes, this is actually exploitable in the instance of your application. All right, I think the clicker died. So some technology background stack. What is Electron? So for the context of this talk, it might as well just be a Chrome wrapper. We're concerned about the underlying Chrome in this talk. We're not concerned about any of the like Node.js side privileged scripts running. We're concerned with the fact that Electron runs Chrome. Chrome is running V8. V8 is vulnerable to CVE 2023-2033. So some details there if you care how Electron works beyond that, but if you're not familiar with it, for the context of this talk, it's essentially a Chrome wrapper. What is V8? So this is impactful because the CVE that is being weaponized is actually a vulnerability in V8 that affects Chrome and can lead to remote code execution in a Chrome renderer process due to how V8 behaves. So it's the JavaScript runtime engine, essentially. It's very complicated. It does a lot of stuff. Very deep level of research people do in actually weaponizing the underlying bugs. And it's notably both an interpreter and it has like 3 layers of just-in-time compilers. So we're going to be taking advantage of those. But essentially what those do is optimize the JavaScript so that if you've got some function in JavaScript that runs a bunch, instead of interpreting it each time, which is slower, it just-in-time compiles into machine code a function that would back whatever that JavaScript function is. And so we take advantage of that later. So what is a type confusion bug? So for context, CVE-2023-2033 is a type confusion bug in V8. So we are not diving deeply into this, but it's just good to know. Essentially, the impact of this is because of the type confusion vulnerability, memory corruption on the V8 heap is possible in such a way that memory manipulation of the V8 heap can be performed. So we are not building that. We're taking public POCs for that, but I'll get there. But it's just good background to have. So the vulnerability selection. The process for picking a vulnerability to try to use to get remote code execution on this Electron instance was a bit of a process. So there's so many things that have dropped. To give you some idea, Chrome 110 came out in March 2023. I was doing this research maybe like February 2024 into March 2024. So there were several end-day bugs within the last year that had come out that could lead to remote code execution. Looking through several of them, I played with quite a few, but I ended up settling on CVE-2023-2033 because it had a public POC that implements V8 heap, address of, read and write primitives. So how those are implemented is well beyond the scope of this talk. That is very deeply technical, and this talk stands on the shoulders of giants working from Misty Mountain Cop's POC to actually implement those primitives for this vulnerability. And there is some reference to the starting point that we're working from, which is that exploit script that implements those primitives. So I had to set up a test environment for the purpose of this talk, I guess, because this talk is talking generally about Electron, and I can't target the production application that I did the original research on. So this was set up. So it's running an old Electron version, Electron 23.2.0, so that is the version we're targeting. And it is very simple. It's just creating a new browser window, notably with the sandbox false web preference set. So this disables Chrome sandboxing, which if we had to deal with, that would be another step of trying to break out of that, and that would get very complicated. Fortunately, in the actual target application, there was no Chrome sandboxing done on the main renderer window, so that is also beyond the scope of things we have to worry about. So essentially what that means is if we get remote code execution in the browser renderer process, it is unsandboxed, and we can do whatever we want on the system without worrying about trying to get out of a Chrome browser renderer sandbox. And so, yeah, we just have this hitting a local web server that pulls the HTML and JS from a directory that we want it to run. And then for debugging purposes, I would attach GDB to the Electron renderer process. So the first step is getting Misty Mountain Cop's POC heap primitives working in Chrome. So these were written for D8, which is V8's developer shell, and they were not built to target a production Chrome instance. So a production Chrome instance calls V8 with very different flags than just running V8 or D8 directly. And so sometimes the way that preconditions need to exist for these vulnerabilities to be exploitable occurs. Sometimes it's not going to work without very dubious preconditions. So fortunately for the case of this exploit, sometimes there's things that are done in the D8 level native syntax to set up those conditions. In this case, there was only D8 syntax for debug prints, so I removed those all because those are not going to run in a browser JavaScript context. And I replaced all the calls to print with console.log because interestingly, when you call print in a Chrome context and not a D8 context, it opens a printing prompt, and that's not helpful. So I ran this on our test application that I set up, and instead of the primitives installing, we just get an error, like a JavaScript error, and the primitives don't install. So again, this could be just due to differences in the environment that the POC code was written for. It might not actually work on real Chrome. It might work in theoretical conditions. Fortunately, if you just beat your head against the problem and try harder, running it 4 times, the 4th time, magically the primitives install correctly. So I don't know why that is. It has to do with the way that they are implemented, I'm sure, and the way that V8 behaves, but that is very deep and well beyond the scope of this talk. But yeah, so modifying the script, adding some set timeouts to the function that installs the primitives, and letting it run 4 times. On the 4th, it works, primitives are installed, and we've got the first step of getting that POC code working. So we have V8 heap primitives. We can read from the V8 heap, write to the V8 heap, and get the address of JavaScript objects on the V8 heap. How do we get remote code execution with that? So there's a lot of research on this online, and it's kind of changed over time. Originally, there were strategies that involved taking advantage of WebAssembly, RWX segments that you could interact with from the V8 heap, and you could just write your shellcode in WebAssembly and jump to that. There's new methods now, and there's also V8 heap sandboxing that kind of makes some of the interactions from V8 heap to like real native heap trickier. But we were able to work from some research from GitHub, and that research from GitHub points at some research from MEM 2019 for a DICE CTF challenge. So in the DICE CTF challenge, they are working with very similar V8 heap primitives and are trying to get remote code execution in an interactive V8 environment. So it's not targeting a production Chrome instance. But the theory here is that we can include a JavaScript function that includes a bunch of 64-bit float values. We can force the JIT compiler to optimize that function and compile it. That shellcode that will be generated will include these long move abs instructions. I'll show this later. And our shellcode will be inside of those float 64 values. So we'll have 6 bytes of shellcode in that 8-byte float 64 value, and then a 2-byte jump into the next chunk of shellcode. So I'll show pictures. Using some code from MEM 2019's research, we get a starting point for just some really basic shellcode that just executes binsh with no arguments, and then encodes it in such a way that you get these 8-byte chunks of shellcode with jumps at the end to jump into the next piece. So that shellcode can be run through, the output of packing the shellcode into those 8-byte hex chunks can be run through a long hex to float 64 converter. So we're just re-encoding it as these values, and then taking this foo and f function and making sure they're aligned in such a way that's necessary from MEM 2019's research. We can lead to the generation of shellcode, or of native code that gets compiled by the JIT that looks like this. So what we need to do to achieve shellcode execution is modify the start of a function, modify the code pointer of a function object to point a little bit further into the JIT compiled code than intended. So showing the actual code that gets generated by the JIT compiler for the foo function, we see here stuff happening. This is what we're interested in. These are the values that we saw output from here that we turned into float 64s. And so now we basically get these very long 10-byte instructions that move a long immediate value into a register. And so what we want to do is, instead of execution for the function starting here, we want execution for the function to start right 2 bytes into that first move QR10 instruction so that it will start executing our shellcode. So this is possible due to variable length instructions in x86. So the immediate value, if we have the instruction pointer pointing at it, that memory will be decoded as instructions that they are not. So we'll have this running, this shellcode that makes the syscall to exec binsh instead of the moving in a long immediate value into R10. So the first thing we need to do to even try to do this is see if we can actually get control of the pointer of the function object on the V8 heap that controls where the code flow for that function is. So we have our foo and f function that we have set up here. So foo is the one that gets forced to be JIT compiled. F just returns 123. So what we can try to do first is, based on the knowledge we have from MEM 2019's research, it says that at the start of a function object struct in memory, you go 0x17 bytes after, and you get a pointer to the JIT address that's used for finding the code for executing that function. So if we perform some reads with our primitives, we can get the address of foo, we can get the address of f, and then if we look at what exists in memory 0x17 bytes after that, so reading like a struct field, we can see that we're able to perform those reads without it crashing, which suggests that, number one, the primitives are actually working, and that there's some meaningful data there. So in theory, what we want to try to do now is swap these two values. So swap the pointer used by, we're overwriting the pointer used in f with a pointer to function foo. So if we're able to do that and see that when we call f it behaves like foo, we know that we have some level of control over the code that gets run when a function is called, and that gives us a good jumping off point. So we add some code to perform those writes with the primitives after installing them. So we replace the pointer to the JIT address of f with foo's. So now when we call f, we're actually expecting it to return that array instead of the 123 that foo usually returns. When we call this, we see it is working, nothing's crashing, which is good, and we are getting the result of running foo instead of the result of running f when we run f. So that's nice and all, but we want instruction pointer control. So based on the research from MEM 2019, the data there suggests that if we can control that JIT address, we can control the 32 low bits of the instruction pointer. So to do this, we can patch our exploit script and just write this junk value that's recognizable. We can remove the automatic calls to pwn and do manual calls from Chrome DevTools after attaching GDB to the process. And our expectation is if this actually gives us instruction pointer control, we should see a seg fault where the lowest 32 bits of the instruction pointer match the low 32 bits of our junk address. So we do not see this expected behavior. Instead, we see a different seg fault. So in our case, we see that it seg faults when trying to read memory at RCX plus 0x7. So our instruction pointer here is not, if you look at the low 32 bits of our instruction pointer, it's not what we want. But if we look at the low 32 bits of RCX, it is what we want. And fascinatingly, there's a jump instruction right after where if we are able to control what gets read here, then we can control the value of RCX. And if we can control the value of RCX, it's going to get jumped to, which is going to set the instruction pointer to RCX and lead to us having instruction pointer control. If we actually look at the breakdown here, we can see it's reading RDI plus 0x17. So this is presumably the base address of that function object. So this is essentially reading the low 32 bits from that, which is what we're calling the JIT address in our tests. It's adding R14 to RCX. So this is reading like a V8 heap pointer. So R14 is presumably a value that maps the V8 heap to the native heap. And then here it's trying to read memory at RCX plus 0x7 back into RCX. So we want to understand how this is supposed to behave so we can get a feel for what is even going on in memory and how far out we are from actually getting to that compiled JIT code, how far down the pointer chain we have to go. So what we can do is, instead of writing our junk value, we can write the original JIT address, but or it where the high bit is set, hoping to see another segmentation fault. And based on that, we'll be able to get back to what the original addresses should have looked like. So if we do this, we do see we get another seg fault reading from RCX. We can take that value and AND it with the inverse of what we ORed it with and see that this was originally what was intended. Mapping it with R14 to the native heap and adding OX7, this is the value that should be read and jumped to by that jump RCX instruction. And so, sorry, this is the, yeah. And when we look at what's contained here, we see this pointer. So this pointer is a pointer to executable code that is intended to be jumped to, presumably generated by turbofan. I think this explains that. Yeah, so if we look at what's at that final address we ended up with, we see something that should look familiar. It's a different disassembly flavor here, actually, or a different assembly flavor here compared to earlier, but we see that we get those long moveabs instructions with those long 8-byte immediate values, and this is the start of our foo function as it got compiled by the JIT. So this is exciting for us because we know that if we jumped into the start of one of those moveabs immediate arguments, we would be executing our shellcode. And if we can control what's going on with the memory that decides where we jump to, so if we can control what gets read here, we can add to that enough to jump into our shellcode. So doing some math, looking at the difference between the start of the function and where our shellcode begins. So in the immediate value here, we can even use GDB to disassemble 3 instructions at that address. And we'll see that it decodes to the start of our shellcode. And we see that that's OX7C bytes further into the function than it's intended to run. So what we want to do is read the value that would be read I've covered this, yeah. So we want to read the value that would be read at that OX7C bytes after the fujit address that we read, and add 7C to it and write it back to its original location. So this is all memory on the V8 heap, so we're able to perform these writes. If we look back at the way it gets called, we can tell due to the fact that this is offset by that R14 value, which is used apparently based on what we've seen to map from the V8 heap to the native heap. So this code will lead to, when we call foo, it'll jump 7C bytes further into the JIT compiled code than intended, which is putting us right in the start of our shellcode chunk. So if we actually set this up, run this, and let it go, we will see that our shellcode successfully executes. Because it was jumping, instead of execution jumping into here where the function should begin, it jumps into this immediate value and begins executing our shellcode that is contained in those immediate values. And so these end with a jump that jumps into the next chunk and so on. Yeah, so this is what we get. This is a very good screen to see throughout all of this. So render process gone is good news. It means that our exec syscall ran and it replaced the Chrome renderer process with binsh. If we look at the GDB we have attached, we see that it did indeed. So on our system, binsh is actually a symlink. So yeah, and again, notably, this exploitation was done on 64-bit Linux. So the available options for the desktop client were Mac, Linux, and Windows, and I chose to build this on Linux because that's what I'm more familiar with. And this is like AMD 64 as well. But yeah, so we've got the basic shellcode working. This might not be enough. for us to show the impact we want to show to the program. This is not a useful payload for us to run. There's nothing we can interact with. It's very limited. This payload was really built to run against like an interactive V8 shell versus like a production Chrome instance. So we want to write more useful shellcode that calls binsh with arguments, that pulls a remote shell script from a web server and executes that, because that'll show we can do literally anything. So the following shellcode was written that calls binsh with this argument, which just grabs a shell script from my web server. And I wrote shellcode to actually do this by hand that met the requirement of having instructions that were all equal to or less than 6 bytes so that we can fit them into those 8-byte moveabs immediate chunks. So this is the shellcode. It's not great, but also it meets the requirements, and it, again, just does this. This is what this shellcode does. It sets up to make the syscall, sets the stack up in such a way and gets the pointers to all the addresses in the right registers to make the syscall to execve. So I put an int3 instruction at the beginning so that when we have GDB attached, we'll hit that and break on it so we can see what's going on a bit better. And so the script was rerun. It output the hex 8-byte values, ran those through a float64 encoder. And so now this is what our foo function looks like. So this contains our longer shellcode, essentially. So there are some twists here. So due to the amount of entries in the array, the turbofan compiled code actually looked different. So instead of the first immediate value appearing 0x7c bytes in, it's actually 0x82 bytes in. So things were tweaked and modified for that. We used the same method as earlier to work out where we were. And so that modification was made, and the exploit is rerun now with this shellcode. But unfortunately, it doesn't work. So we are able to hit the int3, but when we continue, our shellcode segfaults. We were really hoping to see binsh execute, but instead our shellcode crashed. So trying to work out why this is going on, we have to do a bit of digging, but what we find is that the moveabs instructions with those 8-byte immediate values spaced a consistent distance apart are not always present. So if we actually inspect some of the memory, instead of seeing nice, consistent distance apart moveabs instructions, we now see some stuff going on in between where it's storing some of these long values in long registers and just copying from them as needed. Well, this kind of makes sense. So turbofan that we're using to generate this code is V8's top-level compiler. So it's meant to generate the most optimized JIT code. So it makes sense that it would make optimizations like this when compiling a float64 array return for a function. So the problem with this now is that we need to modify the way that our shellcode is generated so that it doesn't repeat itself. Because if we look back to our shellcode, we will see plenty of repetition. And I don't want to write shellcode that doesn't repeat itself and fits into those 6-byte chunks. So we can do some tricks to make it not repeat itself. So we're writing what I'm calling an anti-optimizing shellcode generator. So that Python script we started with, we need to modify it so that we generate unique values for each piece of shellcode. So the way that it works stock is takes 6 bytes of assembly, adds a jump at the end. If there's like extra space, it just fills it with nops. And so that execution might include a ton of nops. Instead, what we do is make sure that none of our repeating lines are 6 bytes. We make sure they're all less than 6 bytes. And we can fill in junk bytes and move the jumps to right after the instructions. So instead of filling nops in between our shellcode and the jump, we put the jump right after, and then we add junk bytes that just get jumped past by the jump. So we do have to calculate different jump values instead of using a consistent value the whole time. But this will, this will mean that the longer shellcode will have those junk bytes, and it won't be able to be optimized by turbofan because each line of shellcode will be, that gets generated by the Python function will be unique. So this is the modification we make. So it procedurally generates bytes based on a counter to try to get unique-ish ones, and we fill in the space between our actual code and the end of the 8 bytes with junk, and the jump goes right after the code. So we can run through the modified script, get our output, run it through a float64 converter again, and replace the contents of the foo array. We can rerun it and see our int3 breakpoint is successfully hit again, so it's kind of a given with this so far, like we've got to the point where that's stable. But when we continue and run the exploit, we do not see binsh executing with the desired arguments. And instead, we see the program segfaulting. So if we look at the instruction pointer, we see that there's good news. There's a normal-looking moveabs instructions instead of the past instance that looked more like this, where you've got all these movesd instructions in between and using other XMM registers where the original, whatever first time that we saw, like a push RAX, it's just copying from those for all the repeating lines. But we do see that this looks good. Now it looks good, but if we look at what's actually going on here, we're getting punished by the very thing we're taking advantage of with this, where due to how x86-64 instructions work, they are variable length, which is the only reason we're able to execute immediate values of moveabs instructions. But the size changes between the two. So these may look the same, but this actually takes an argument with more bytes now because it's using a longer value. So doing some math on this, we can work out that this begins occurring after the size of OX14, so the gap between these two, is consistent for the first 15 instructions. After, or sets of instructions, first 15 moveabs instructions that have those immediate values that contain our shellcode. But after 15 of these, the jump size changes to OX17. So we can account for this in our shellcode generator, where instead of always using a fixed value and assuming that it's always OX14, if we've made over 14 instructions, then we actually add another 3 bytes to that jump instruction. So running this through the converter, we're able to see that the shellcode is executed successfully. We rerun all of it, get the final payload running, remove the int3, and we see that we now have the execution of our staged payload. So our staged payload just contained the content of bin touch, temp RCE POC, and we see that that file now exists. So notably, if we were running in a context of a browser window that had the Chrome sandbox enabled, we would not be able to do this because we wouldn't be able to just touch the disk like this because we'd be in the Chrome sandbox and we'd have to try to figure out how to get out of that, which there are vulnerabilities that impact Chrome sandbox safety that affect this version of Chrome, but weaponizing those would probably suck. So fortunately, we don't have to do that. So we can see now that the stage script has been pulled successfully and that the exploit mostly works, heavily relying on the V8 heap primitives implemented by Misty Mountain Cop and using techniques inspired and adapted from MEM 2019's research. So the big piece that deviated from MEM 2019's research is the fact that we had to perform the additional OX7 byte difference. So on the Chrome version that MEM 2019's research covered, that JIT address would have pointed directly to the JIT shellcode. In this case, it appears to be a pointer to a struct that includes the actual, what we call the code address, OX7C bytes after. So that was a place where we saw a deviation from the expectations. Right, okay. Yes, so fully weaponizing this. So we now have a working proof of concept JavaScript file that when it executes on a browser window on the old vulnerable Chrome/Electron version, we got binsh to run our stager shellcode that pulls a shell script from our remote server and execute it. So there's some issues still here yet. So the primitives don't always set up properly each time. They're really good. That's why they're able to be such a black box, because Misty Mountain Cop did such good work with those. I don't have to know how they work to use them. But they do crash about maybe 10% of the time. So to mitigate this, I created an exploit loader.html file that iframes 5 instances of exploit.html. So this exploit.html includes the actual exploit.js that has the exploit code. So we're essentially just shotgun affecting it and just trying to run the exploit 5 times. Maybe 1 or 2 of them will crash, but 1 of them will probably work. And so this will give us more consistent execution of the RCE POC payload. Notably, we don't have to worry about being loud. We don't have to worry about running our shellcode multiple times. We're just trying to prove that RCE execution is possible on this platform, because that's really all that matters for the bug bounty context. And as long as we have a working proof of concept, even if it's noisy, even if it's stable-ish but kind of runs multiple times, that's still showing the needed impact. So the final versions of the files I've mentioned can be found here. So I might pull these up and we might be able to look at them. But this is all available online. I also have a blog post up about this. But yeah, so conclusion and some takeaways here. So we kind of ran into 2 realities that were a little bit different than what we were intending to see. So we saw that the Chrome bug that we wanted to exploit relied on theoretical assumptions that POCs used from V8. And so getting those to actually work on production Chrome was a little bit of a difference. And getting the longer shellcode to run was tricky. So the original research that we started from had the very naively implemented, but I mean practical shellcode generator. So we started from this and amped it up quite a bit to be able to work around turbofan optimization for longer shellcode, and then also the longer gaps in between. So if we look at the original shellcode generator, we see it's always using a fixed jump instruction. So this jumps OX 14 bytes after. So we had to change that assumption. We had to not repeat shellcode lines. So we had to build our generator for that. And we had to expand our shellcode into something practical. Yeah, so the way that this went, I was able to get the RCE POC working on the actual desktop client. I was able to get a vulnerability report submitted on HackerOne. The company fixed the bug, and they paid out for a critical remote code execution bug, which was excellent. It's not disclosed, so I can't say who it was or what it was, but it worked in practice, which was great. So showing the actual exploit code, the final code, we can see some of the items that I touched on. Whoops. So we see our final foo function here, so that includes our encoded shellcode. These get translated into those long move abs instructions by the JIT compiler. And then this ends up being our final pwn function. So again, we are reading the foo address value, so that is the function that is JIT compiled. We're reading down that pointer chain to eventually get to where the pointer to the native code is stored. And then we modify that pointer to the native code to jump a little bit further into it, and that leads to the shellcode execution. And then the final version of the shellcode generator script can be seen here. So we now, instead of having the consistent jumps, the jumps get generated by calculating how far we need to jump. Yeah, so the jumps get generated by that, so we work out how much to jump. We count how many of these instructions we've made, so we know when the instruction size is going to change, and we have to add that extra 3. And then we have our long assembly code that gets encoded with this process. And then at the beginning, we have our shell code, or our shell instructions and our shell arguments that end up getting pushed onto the stack before the syscall to execVE, and things are set up in a compliant way for the syscall. All right, oh, this is very funny. So looking this bug up, you get this response in Google search from pulling from MSRC, and it says you need to enable JavaScript to run this app, which is pretty funny when it's a bug in a JavaScript engine, and it's kind of sketchy. Do we have any questions? Yes?
Hey, first of all, Nick, your persistence in getting that shellcode to work is awesome.
Thank you.
So did the vendor fix presumably involve shipping with an updated patched version of Chrome along with running it?
This is a great question.
Sandbox mode?
No. So what the vendor did, and I'm not happy about it, but it technically, when I retested it, I couldn't reproduce it. So instead of patching the Electron version they're running and considering not running with sandbox mode enabled, as was included in the report, which isn't disclosed, no, they were just like, yeah, we'll patch the XSS bug, and that's all we'll do for now. I have not looked back to see if they've gone in and updated the Electron version to not be running an old vulnerable version of Electron, and I have not checked to see if they've changed the configuration for the browser window to run sandbox true. I doubt it. Honestly, I doubt it. They're actually having some trouble right now with their platform, and they're losing people because they made some change to their terms of services. They probably have bigger things to worry about than security, which is pretty funny. Any other questions? Cool, all right.